Good afternoon.
Good afternoon.
Who said good morning? You need to go home and take a nap.
Oh, that was me.
All right. You need to go home and take a nap. As obviously you...
Well, if you say so, I'll just head out.
Well, I didn't say right now, but you know. All right. Well, how's everyone today? I think everyone survived the test.
Just barely.
No.
Barely. Not really.
We're taking it after class, right?
Oh, you're taking it after class. That's right. Okay, so I guess we'll not talk anymore about that. So, yeah. I've got it set up for you. Yeah, after it. All right. So let's see. We're all there in Winslow. How about St. John's? They must still be taking it or something. Let's hope they're here. All right. Let's see. Are we missing anybody in Mogollon?
No, everyone's here.
Okay. All right. Well, we'll just kind of wait. All right. So we got, somebody came in and left. Oh, now they're coming in. Okay. So I made an executive decision and I actually didn't get a vote from you on this one because I had to make the decision this morning. But I really feel like that with taking the test today, and then I wanted you to do the quizzes before the midterm next week, that I decided to go ahead and make tomorrow a Moodle day. All right, so I'm not gonna broadcast a class. Now I'm actually leaving those last 4 quizzes from chapter 3. They're actually going to be open all weekend. So what I would like you to do is use the class time tomorrow to take as many of those quizzes as you can. All right. So what we've got is the last 4 quizzes from chapter 3. So 3.6, 3.7, 3.8, and 3.9. So if you get 2 of them done, or 3 of them done, or 1 of them done, or whatever, it's okay. Because I've got, like I said, I've actually got until I've got them open until next week, until next Wednesday when we start the midterm. Okay, so there'll be no class tomorrow, no broadcast tomorrow. I would like you to use your time to work on quizzes, to prep for the midterm, that kind of thing. Okay? So, but you won't see me tomorrow. After today's class, then I won't see you till Monday. All right? So, are we all okay with that? Okay?
Here in St. John's, us 3, we didn't get to our second attempt
Of
the test
today, the chapter 3 test?
Yeah, I didn't even get to finish my first attempt.
Okay, then you need to pick up the pace. Okay, now I'll open it again for you, but if you're going to need to look up less stuff and you're going to need to practice and study more before you take the test. Okay, now having said that, this morning I proctored a group of calculus students, and most everybody was doing it. It was taking them between 45 and 60 minutes to do the whole thing. But one of the quizzes, though, I think it was the 3.9 quiz, they were finishing in under 5 minutes. So sometimes they go quickly and sometimes they don't. But in general, you need to have more practice under your belt, and so you know, okay, I've got to do that. So if you will email me when you guys can take the second attempt or whatever and reproctor, if you want to do that during class time tomorrow, that would be fine.
Yeah, class time tomorrow.
Can we do it exactly the same time tomorrow?
Yeah, the same time tomorrow as we did today. So
okay, sure. Yeah, that works. That works. Okay, let me make a note of that. Same time Same gem. All right. Okay, so today the plan is we're going to go on to 4.2, and then Monday I'm also preparing lessons from chapter 4 to go on to new material. But as you know, if you need any review or me to go over anything in preparation for the midterm, I'll be happy to answer questions and so on. So unless anyone has a question right now, I'm going to go ahead and start. Okay. All right. Let's do it. Okay. So 4.2 is where we are.
Good.
Hey, Mr. Strong, do you actually think that you could go over the chain rule really fast?
Sure. Yeah. Yeah. Is there a problem, or you just want to kind of review it in general?
Well, it was just a problem on the test, so we can't really go over it, you know.
Okay. Sure. Okay. Well, let me just kind of pick a problem in general. Okay. Let's do. Okay. I'm going to do one that has like two links in the chain, so to speak, where you have to use the chain rule twice. Okay? Oops. So let's say we have y equals sine squared 5x. Okay? Now, first of all, when I'm doing derivatives on trig functions, when there's a power, I kind of like to just rewrite it as like sine of 5x squared. Because to me, it's easier to see with the chain rule, you're going to work inside out. Okay, so then to take the derivative, I would bring the 2 in front times the blob. So you don't change anything inside here. So that's the sine of 5x. And then we can write through the first if we want, but we don't need to. But then now times the derivative of the blob, the inside part. So the derivative of sine is cosine. So that's going to be cosine 5x. So that's the chain rule. Well, now we got to use the chain rule again. We got to multiply by the derivative of this inside part. So times 5. All right? And then so to clean it up, we could just put the 5 with the 2 and say y prime equals 10 sine 5x cosine 5x. Okay, I really don't, I don't need that set of parentheses right there. And really, you don't even have to have parentheses around the 5x either. Okay. All right, does that help, or you need some more?
It's
So, Mr. Strong, can we also go over? So, on the test, there's a question with a table, and we have to use the table to find the derivative. How do we do that? I don't think we've gone over that, and I think a lot of us are confused on how we would go about that.
Well, okay, so use the table, all right. So that was where see, let's say if you have I don't know, we'll just make up some values here. So I don't even have a function. Okay. And let's say I'm going to try to use the table to approximate the the derivative at, I don't know, one of these x values. Okay, doesn't matter which. Let's say f prime of 0. Okay, so what you're doing is it's like you're looking at the slopes as they approach this point. Okay, so you use the slope formula. So the difference in the y's over the difference in the x's. So if we use, let's say, these 2 points, okay, then the slope would be, so I'm going to call this M1. The difference in the y's would be 7 over the difference in the x's would be -1. So that would be negative 7. All right, then if we look at the slope of these two, then it's so we'll call that M2. Then here the difference in the y's, 19 minus 20, would be -1 over 1 minus 0 is 1. So that would be -1. So then the slope of at the point 0 has got to be between -1 and -7. Okay. Now, if it's,
Would
let's
the slope,
say,
would
go
the
ahead.
slope of M1 just be 7 because it's -1 minus 0 would be -1?
0 minus negative.
Or, yeah, 0 minus -1.
Of M1?
Yes.
Oh, 0 minus, oh, you're right, thank you. Okay, so then the slope of what we're looking for here, the slope at 0 would have to be between those two. Okay, now if you're given an endpoint, then you're not going to be able to say it's between these two. So there, what you do is you see if there's a trend. You'd like take the slope of these two, these two, these two, and see if the slopes are approaching a number. That was kind of how we started with limits. So yeah, we did do that. We talked about like fruit flies, and then there was a car example, and we did that in chapter 2 and chapter 3.
Another question. So
Okay.
there was another question, and then it had like, it gave us like f of x at this point equals this, and then g of x at this point equals this. So it had like that listed, and then it wanted to know like the f of g of x, but it didn't give us like all 3 or all 4 to figure it out. Like, how would you? Am I making sense?
No. Is it asking for the derivative?
Yes. So it was.
So is it like a product where it asks you to find the derivative of a product?
Yes, but it didn't have. So it only had 3 values. So it did f of x at this point equals this, g of x this point equals this, f prime of x equals this, but it didn't give you the g of x, g prime of x.
Yeah, I don't know. I would have to look at that. So that's on the chapter 3 test? Okay.
Yes.
I'll take a look at that. If there's some missing information, then I'll certainly give you credit for it. I'll tell you what it sounds like to me. All right, it sounds to me like from section 3.3, practice 5.5. So you might take a look at that and see, but if there's information that's missing, then I'll give you credit for it. But otherwise, it sounds to me like you would want to study practice 5.5 and see if you remember how to do that. All right. Anything else?
Mr. Strong,
Yes.
what does it mean f squared of x?
X squared of x.
No, f squared of x.
Oh, that means to take the second derivative. Okay.
Also, can we go over how to get the slope of a tangent line at a certain point?
Well, this right here, if you're given specific points, then you just do the slope. Use algebra. If you're given a function, then you take the derivative. Okay, and that's the slope of the tangent. So more than likely, that's what the question is wanting you to do. Is take another meaning of the derivative is the slope of the tangent line. So if you take the derivative, that gives you the slope in general, and then you plug in that specific x and or y value, and that gives you the slope at that point. Does that make sense?
Hang on. Hey, can you go over that again?
Sure. Okay. All right, so let's say we have the function f of x equals x squared. All right, and a point on that line would be 3 squared is 9, so 3, 9. All right, so so the derivative f prime of x is 2x. So that's the slope of the tangent at any point. So at that point, you plug in the 3 for x. So the f prime at 3 is 2 times 3, which is 6. So that's the slope of the tangent at that point.
So how do you find the equation for a slope of a tangent line?
Okay, so then you got to use the point slope formula. Y minus y1 equals m times x minus x1. And so then you say y minus the y coordinate, which is 9, equals the slope that we just discovered, 6, times x minus the x coordinate, which is 3. And so then that gives you y minus 9 equals, well, okay, so that might be the answer right there. But a lot of times they'll put the answer in slope-intercept form, the line. So if we put it in slope-intercept form, we distribute the 6 and then add the 9. So we get 6x minus 9 is the equation of the tangent at that point. Okay, so let me suggest, so for class on Monday, as you're going through, I know you're going to be working mostly in chapter 3, but really, if there's any of the practice problems, it will actually, you'll learn more if it's a problem that you've attempted versus a problem that I'm making up. Because if it's one that you've attempted, you'll see how far you go and see exactly what it is that you didn't understand. Okay? And you'll get a lot more out of it. So if I could just suggest that you do some practice problems to study and from the different homework from the different sections, and then ask me to do specific questions. And I think that will be a better review for you. Okay? All right, well, let's go ahead and go on to 4.2. All right. Let's see, okay, so we're talking about the mean value theorem. And we actually start off with a corollary or kind of a side theorem that we get from the mean value theorem, and this is called Rolle's theorem. Okay? Now, Rolle's theorem is actually a very important theorem in math, is it helps us to find zeros and tangents and that a lot of different things. So let's look at what Rolle's theorem is telling us. It says suppose that f of x is continuous at every point of the closed interval AB and differentiable on every point in the interior. Now, I've kind of breezed through that kind of stuff before, but with Rolle's theorem, you kind of actually have to show that all three parts are true, that the function's continuous, that it's on a closed interval, and it's differentiable on the open interval. So that means everything but the endpoints. Okay? Then what Rolle's theorem says is that if f of a equals f of b, so two y values that are the same, then there's at least one number in there in the between where the derivative is equal to 0. Okay? So that's saying like here, if you have these two y values the same. However you connect the dots, like with this or like this or like this, somewhere you're going to have a horizontal tangent. Okay? Here you have two. Here you have a lot more. So you might have more than one, but somewhere you're guaranteed to have the derivative equal to 0. Okay? Now, if let's say the two y values are the same and you connect them with a straight line, then would you have a horizontal tangent to that?
Yes?
What would it be? The whole horizontal line. See, that tangent would be 0. So when we're saying that the derivative is 0, the slope is 0, that's the same thing. Okay? All right, so if we want to prove that Rolle's theorem is true, okay? So what we need to do is say, okay, here we have a closed interval for this polynomial. All right, now, all polynomials are continuous. So if we just have a polynomial, it's going to be continuous. And then it's also differentiable. All polynomials are differentiable. Okay? So what that means is just to show that it satisfies it, you kind of state this. And then if you want to actually show that it has one, then you take the derivative, set it equal to 0, and solve. And so, yes, the derivative was equal to 0 at not 1, but 2 points. Let's see, actually this should be square root of 3. Plus or minus the square root of 3 is where it is. Okay? So, see if you can do practice 1A. About Rolle's theorem. Okay, so, all right, so you have a polynomial here. So it's going to be continuous. All right? Do you remember, like, if this was a trig function, what trig functions are continuous? What are the two continuous trig functions that are always continuous?
Sine and cosine.
Sine and cosine. There's no vertical asymptotes, okay? But anyway, all polynomials are continuous, okay? And then the polynomials are differentiable, and you have a closed interval, all right? So then you can say that there is somewhere where this derivative is 0 in that interval. All right, so if we take the derivative, set it equal to 0, then, Joran, what value for x is the derivative of 0?
0.
0. And see, 0 is in this interval between -1 and 1. So at x equals 0, the derivative is 0, and so it satisfies Rolle's theorem. Okay? So this is important to help us find things like zeros. Okay? Now, the next example is the idea of Rolle's theorem can be used to show that a solution exists for the original function. Okay, so a 0 exists for the function. All right, so the key here is to say, all right, if we look at this derivative, okay, all right, so here we take the derivative of this function, and if we're looking to see where the derivative is 0, actually for this one, there is no place where the derivative is 0. So what that means is that the function is always increasing. And see, when you think about that, because see, when the derivative is 0, that means it's get like leveling off and going to come back down. So if the derivative the function is always increasing. See this 3x squared plus 3? See, no matter what value you plug in for x, that's positive when you square it. And you multiply it by 3, it's still positive. You add 3 to it, still positive. So if the derivative is always positive, that means the function is going up. And it doesn't ever come back down. So the function is always increasing. So what does that mean? That means that, see, we know it's odd positive. So from the function dance, you know the graph goes like this, okay, like this. And the fact that it doesn't come back down means it only crosses the x-axis one time. And so there is exactly 1 0, exactly one x-intercept and no more. Okay? So we get that if the derivative is always positive or always negative, that means it can only have one solution. All right? So see if you can figure out what's the deal with practice 1b. Is the derivative always positive? Is it always negative? Is it 0? Can you not tell? Just see what you can do looking at the derivative. All right, so Joran, what do you know about that derivative?
It's always going to be negative.
And so what does that mean about the function?
It never crosses the x-axis.
Well, it will cross one time because, see, this is odd, negative. And remember the function dance in pre-calculus, odd negative, it starts up and then goes down. But see, the thing is we don't know just from that, just from pre-calculus. I mean, we know it goes like this maybe, but it could go like this. You know, so it could have tons of x-intercepts. But the fact that the derivative, well, I don't know. Okay, so look over here in green. We don't need this part over here. So this derivative is always negative. So that means if the derivative is negative, that means the function is always going down. It's decreasing from left to right. And so it doesn't, see how I've drawn this where it goes down and then comes back up? It doesn't do that. It just goes down and never comes back. And so that means you only have one solution, one x-intercept, 1, 0. Okay? All right. Any questions on that? Now, by the way, your calculator uses this idea when you do second calc 0 and you do left bound and right bound. So your calculator knows, hey, there's just if there's just 1 0 in there, that it knows to find that. It's kind of programmed with that idea. We'll talk more about how it kind of zeroes in on it. Okay. All right. So next, the mean value theorem. So the Rolle's theorem is kind of an offshoot of the mean value theorem. But the mean value theorem says that if y equals f of x is continuous on a closed interval, differentiable on the interior, so the same hypothesis, then there's at least one point in C at which, and okay, so see this right here, this is the formula for slope from algebra. So this is just saying, okay, you've got 2 points. Here we're calculating the slope of those 2 points. And we're saying that that is equal to the derivative at some point C. Okay? So visually, this is what I think the visual for this is more helpful than any of the words or even the formula. So this just says, look, if you have any 2 points and you calculate the slope of those using algebra, that somewhere along the curve, there's a derivative equal to whatever we get for that slope. Okay? So here I've actually drawn in 2 places where the slope of the tangent, the derivative, is equal to the slope of those 2 points. Okay? So you use algebra to find the slope of the 2 points, and then you use calculus to find where those points are the same. Okay? So let me show you that. So the math in these is usually pretty straight up. Okay? So here's our function. Now, my interval is 0 to 2. So those are my 2 x values. So the first thing you want to do is find the points so that you can calculate the slope. So you plug in these points into the function. Okay? So still algebra. So 0 squared is 0. 2 squared is 4. So that means my 2 points are 0, 0, and 2, 4. And so now I use algebra to calculate the slope. And so I get the difference in y's over the difference in the x's, and I get a slope of 2. Okay, so now what the mean value theorem is stating is that somewhere there's a value for x that has a slope of 2. So to figure out what x is, we take the derivative. Okay? So the derivative, so f prime of x is 2x. So we take that derivative and set it equal to the slope. 2x equals 2, so x equals 1. So that's the answer. That's the value for x that has the same slope as the endpoints. Okay? All right, so see if you can do practice 2. All right, so Rhett, what is our M?
Is it undefined?
Well, let's see. If we plug in these values into the function, and so what happens is we get a 0 for each of them. So -1, 0, and 1, 0. So when we calculate the slope of those 2 points, it's 0 over 2, which is not undefined, but 0. Okay? So when you subtract the x's and you get 0, then that would be undefined. This is where you just have a slope of 0. Okay? All right, so Skylar, when you get the value for x that has a slope of 0, that's what I want to know next.
Is it 0?
Is it 0? It is 0. Because here you take the derivative, and so when you set that equal to 0, okay, a fraction is equal to 0 when the numerator is 0. So you can just ignore the denominator. And so you get -x is equal to 0, so x is equal to 0. All
Can
right?
you just go over how you got the derivative for
Sure. Okay, so when I have a radical, I like to rewrite it in exponential form to do the derivative. So the square root, that means to the 1/2 power. So then to take the derivative of that, I bring the 1/2 in front times 1 minus x squared to 1 lower power. So 1/2 minus 1 is -1/2. And then you use the chain rule and multiply by the derivative of the inside part, which is -2x. So then the 1/2 and the 2 will cancel. So you have -x, and then I use the elevator rule. If you have a negative exponent, you can bring that to the bottom. And then 1/2, I just put that back in square root form. And then, like I said, when you're trying to figure out where is that equal to 0, all you have to do is worry about the numerator. Because if the denominator is 0, then it would be undefined. All right? Okay. So, a physical interpretation of the mean value theorem says, if we think of f of b minus f of a as b minus a, so that's the slope. So that's the average change. And then f prime is the instantaneous change. Then the mean value theorem says that some instantaneous change has to be equal to the average change. So the first day of chapter 2, when we were talking about average change versus instantaneous change, so average change is the slope, the algebra, instantaneous change is the derivative. So the mean value theorem says somewhere that derivative is equal to the slope. Somewhere the instantaneous change is equal to the average change. Okay. All right. So here we have. So actually, I want you to focus on this example, and I'm just going to have you just delete practice 3. Okay. Just delete practice 3. So here you have your car starts at the beginning of a test. It's stopped. So at time 0, the distance is 0. Then after 8 seconds, it's gone 352 feet. Okay. So to calculate the average velocity during those 8 seconds, we take the difference in the y's over the difference in the x's. And so you get 44 feet per second, which is approximately 30 miles per hour. Okay? So what that means is somewhere along the way, you had to have been going 30 miles per hour. At some point, the derivative, that instantaneous velocity, was 30 miles per hour. Okay, so let's say you're an officer for the highway patrol, and you pull over a semi. All right, and they have to have what they call a logbook, which basically says that they were at a certain place at a certain time. And then as an officer, you examine the logbook. And you see that, let's say from Hope that the last time they wrote in their logbook was in Flagstaff. And you see that they've gone 100 miles in 1 hour. Can you write them a ticket?
Yes.
Yeah, because even though you didn't see them speeding, you didn't clock them, you can say, well, look, if your average speed was 100 miles an hour, then at some point you were going 100 miles an hour. You have to have been going that. You probably were going a lot faster. But you can legally write a ticket just based on that information. Okay? All right. Let's go to the next one. Okay. So, let's see. If f prime equals 0 at any point of an open interval, then f of x equals c for all x's where c is a constant. Okay. So let's see if we understand what this is saying here. Okay. If you have a 0 derivative, then if 0 is your derivative, then that means your original function was a constant. Because the derivative of a constant function is 0. Okay. Let's see. All right. Do I have? All right. And then here it says if we know that the derivative and we know that the derivative and an initial value. Why do I not have that screen here? Okay, here we go. We know that the derivative and an initial value, with that we can determine the function. So it's like playing Jeopardy, where I give you the answer and you figure out the original question. I tell you what the derivative is and what an initial value is, and you can figure out what the function is. Okay? So let's say I know the derivative is 2x. Then I say, well, what function has for its derivative 2x? And the answer is x squared. Or x squared plus 1. Or x squared plus 2. Or x squared plus c is usually how we write it, where it could be any constant. So we have to be given an initial value to figure out what the constant is. And so this is what we call the general solution when we have a C in our answer. Okay? Now, if I happen to be given an initial condition like a point, 0, 5, then what I can do is plug that point into my general solution and figure out what C is. So if I plug in 0 for x and 5 for y, then I get that 5 is equal to C. And so then y equals x squared plus 5, that's what's called the particular solution. So it's figuring out what the function is that has the that has that derivative. Okay? And so this is really crucial to where we're going to be going next. All right? So let's just see if we can finish off that last practice problem. It says, find the velocity and the position for functions for an object free falling from rest with an acceleration of 9.8 seconds squared and initial height of 100 meters. Okay, so to tackle a problem like this, we start with the acceleration is 9.8. And actually, if it's falling, I put in a negative there. All right, so then what function has that for a derivative? What would the v be? Going back the other way.
Negative x to the power of 9.8.
Well, not to the power, but times.
Oh yeah, times, sorry.
So it's just time. So it would be negative 9.8 x or t or whatever variable, and then plus c. So to figure out the constant, you say, what's the initial velocity? Well, it says the initial velocity is at rest. And so then you say, well, the initial velocity is 0 when time is 0. So that means that c is 0. And so then our velocity function is just negative 9.8 t. All right, so doing the same process, see if you can figure out what the s function would be. What would have its derivative is negative 9.8 t, and we'll pick that up on